This is the answer key to the Pre-Calc Unit 8 test review guide, and the unit covers logarithms and exponential functions. So this first question is very similar to a question that was on the beginning of, I believe it was homework assignment 1, if you want to compare this. But what you're doing is you're looking to see if you can use the properties of exponents to find equivalent expressions here. So, for example, if I were to take this middle expression and look just at the exponent, I see that that's something that can be factored, and so I can rewrite this expression as 2 to the 2 times parentheses x plus 3 power. And then if I just look at the 2 to the second power, that's 4. And I'm seeing a lot of 4s as bases in these problems. So let me pause there for a second and look at one of the other expressions over here. And I know that 64 is 4 to the third power. And 4 to the third times 4 to the x, well, you want to add exponents. If you're multiplying expressions and it's the same base in each with an exponent on each, then you add the exponents. And so this is 4 to the x plus 3 power. So I know for a fact that those two, the second and the third, are equivalent. And if I were to play around a little bit with this one, I would need to somehow make this related to 4 to the third, and I can't. So in this one, that's not equivalent to the other two. Now, again, in this next problem, this is in number 2, it's a multiple choice. So there's only going to be one answer, and you're trying to make that answer, whichever one it is, equivalent to the equation given in the question, 2 to the negative 3 minus x. And so I'm looking for bases of 2 with exponents of 3 or x, and the negatives tell me that there may be some denominator involvement here. So in number 1, I see that 1 over 8 is the same as 2 to the negative third power. So this is 2 to the negative 3 times 2 to the x, and that would be 2 to the x minus 3 power. And since the x isn't negative there, in order to be equivalent to the given expression in the original problem, the x would have to be negative. And so it can't be A. Let's take a look at B. In B, we have 2 to the third over 2 to the x, and that's the same as 2 to the 3 minus x. And in this case, the 3 isn't negative, and there's no way to make it so and still keep the x negative. And so x and 3 would have different signs in letter B. And so B is also not our option. When I look at letter C, I can rewrite the first part, or the first thing multiplied, the first factor, as 2 to the negative 1 to the x power. And I can write the second factor, 1 over 8, as 2 to the negative 3 power. Well, if I were to multiply negative 1 times x here, I get 2 to the negative x times 2 to the negative 3, and then I add negative x plus negative 3 is negative x minus 3, which is essentially the same thing as negative 3 minus x. And so my answer for this question is C. And if you just real quick want to take a look at D to make sure that it's not D. I always do that with multiple choice questions. I'm 99% sure that the answer that I think is right. But I still didn't look or consider one of the 4 options. And so I want to go back and kind of look at that. And what you have here is 2 to the x over 2 to the 3rd power. And that's 2 to the x minus 3. And again, there's no way that you can have both the x and the 3 have the same sign on them. And so it's also not D. In number 3, you need to be able to distinguish between exponential graphs and logarithmic graphs. And remember that the difference, and you might want to make a note to yourself here, the difference is that, sorry, I clicked the wrong thing, and you probably couldn't see it. The difference here is that an exponential function has a horizontal asymptote, and a logarithmic, let me change colors here for a second, and a logarithmic function has a vertical asymptote. So the idea here that you want to look for is where is the asymptote in each of these graphs. And actually what I would do first is just look at the 4 graphs and ask yourself if you can see that each one of them is either exponential or logarithmic, that I haven't slipped a quadratic graph in there or a cubic function or something like that. And so, yes, that's coffee in the background, you know me. And so in this graph, you kind of want to look for the asymptote in an exponential or logarithmic graph. You kind of want to look for the place that has basically straightened itself out. So for example, in this first graph, I see that the end of the graph up here seems to keep going up. It's going up slowly, but it's going up. Whereas the other end of the graph, the end of the graph down here seems to straighten out. So I would place the asymptote on this graph right here, like that. That's a vertical asymptote. And so this is going to be a logarithmic function, and we want to put a box around the logarithmic functions. If I were to ask you a question like this on a test, don't be sloppy about making a box or a circle, because sometimes when I'm grading papers and I've asked a question like this, corners of a box tend to get rounded because the student is working quickly and they end up not making a really good boxy looking box, and then I can't tell. And remember, if I can't tell, I'm not going to give you credit for it. So in the next problem, when I look at this, it seems to me that this end of the graph straightens out and that this end of the graph keeps going to the right slightly, but it keeps going to the right. And so for this graph, I would put the asymptote here, and I would call that an exponential function. So we're going to circle the graphs of exponential functions. In this one as well, I see that it looks to me like this end of the graph keeps going slightly to the right, whereas this end of the graph seems to straighten out. And so I'm going to put the asymptote to this function right about there. And so again, I'm going to circle that for an exponential function. And then over here, to me, it looks like this end of the graph continues to go slightly down, and this end of the graph kind of straightens out. And so I would put the asymptote for this graph right about here. And because it's a vertical asymptote, I would put a box around that as a logarithmic function. I would say that it's not always very easy to distinguish between a logarithmic and an exponential graph. And so you might just want to go to Google Images and just type exponential graphs, logarithmic graphs, and just look and look and look and look and look and look and look at them. And you might not even get every single one of them right. This is not a place where I will try to trick you. Don't spend a lot of time on this, but just know that it's not always super obvious which it is. So number 4, the parent function, meaning the parent function, the function before you have any shifts or flips or transformations whatsoever, the parent function of an exponential function. What you're kind of picturing there for the exponential function is that the graph would look something like this, the parent graph of an exponential function. And so your domain is always going to be all real numbers, and the range, because notice that you don't have any y values down here. So your range is going to be from 0 to infinity, and it doesn't include 0 because remember that that's where your asymptote is. Let me draw a better asymptote. So your asymptote is at 0, which means that over here your graph gets close to 0, but it never actually touches 0, and so you're going to use round parentheses there. And that asymptote, remember that you need to give asymptotes as equations, and so it's going to be y equals 0. Just writing 0 will not get you full credit for when you're asked about the equation of an asymptote. This question is similar, and it asks about a logarithmic function. And so the parent function of the logarithmic function would look something like this. And it has a vertical asymptote right here at 0, which means that it's not going to touch 0, but it will become infinitely close to 0 at the bottom of the graph. And so your domain is going to be 0 to infinity, and your range is going to be all real numbers, and that asymptote is x equals 0. Remember that because exponential and logarithmic functions are inverses of each other, don't forget that the thinking is then that the domain and the range are exchanged when you switch back and forth from a function to its inverse. You're switching the domain and range, or all the x values and all the y values. You will be asked to convert between exponential and logarithmic form. So given a logarithmic equation, you're going to need to rewrite it as an exponential equation. And remember that whatever is the base of the logarithm is the base of the exponent. So it's going to be x to some power equals something. And then that power is always going to be whatever's on the other side of the equal sign. So the x to the power of 30. And then the whole thing equals whatever we're putting into the logarithm. So x to the third power of 30 equals 3y plus 6. And then in the opposite direction, you're going to convert this to logarithmic form. And again, don't forget that the base of the logarithm is the base of the exponent. And so this whole thing is going to be log base e. And remember that the logarithm equals the exponent, and that the exponential function equals the input to the logarithm. So log base e of c equals v plus b. It would be really super fantastic if you also recognize that this would be better written as ln c equals v plus b, because remember that log base e of whatever is the same as ln of whatever. That log base e is ln. That's a funky green thing that just happened to the blue ink. Why does the logarithm of any base of 1 always equal 0 for any valid base a? Valid meaning we're not using negative bases and we're not using a base of 1. So log base anything of 1 is always equal to 0, and this has to do with the fact that the logarithm is the inverse of the exponential functions. So your thinking is any number to the 0 power is equal to 1. The implication here that I didn't put in the directions is that I want this written as a sentence. And so you might want to say log base a of 1 always equals 0 for any valid base a, because any number to the 0 power equals 1. And similarly, in 6b, if you think about, your thinking is log base anything of a negative number is undefined. And that doesn't say theta. Let's just fix that right now. Let's make that a negative number. Is that better? So log base anything of a negative number is undefined because there's no power that you can put on a that would give you a negative answer. And so again, in complete sentences, you would want to say something like logarithms of negative numbers are not defined because there is no exponent you can put on a base. A is greater than 0, a does not equal 1. That would result in a negative number. Now, before I turn the page, I want to point out something that I failed to at the beginning of the video, that at the top of the page, it does say questions number 1 through 9 without a calculator. And you have your little icon, no calculator. And there really wasn't any computation on this page that you would have needed a calculator for. But as we go to the next page, remember that you're not using a calculator. And if you are using a calculator at home, those same type of problems will not be on the calculator part of the test when you take the test in school. So here we have a few questions that are simplifying expressions that have exponents in them. And basically you don't want to have an exponent on your answer, and you don't want to have a negative in an exponent, and you want to get rid of parentheses. So for this first problem, the first thing to remember when you have a negative exponent is that that forces a fraction. And be careful of the mistake of equating a negative exponent with a negative answer. Negative exponent gives you a fraction answer, but it'll still be positive. And then whatever 4 to the positive 3 power is, it just goes in a denominator. So your answer for part A is 1 over 64. I would say have 4 to the third memorized. Don't memorize a whole lot of exponents, but I would say 1 through 12 to the second power, and maybe 1 through 6 or 7 even to the third power, and memorize not is I'm not going to ask you to make a list of those numbers, but just so that you recognize them, because there'll be numbers that keep coming back. And if you recognize that, say, 64 is 4 cubed, when you see that number in a problem where there's a base of 4 and you're looking for a logarithm and you've got to do a bunch of other things, that's something that might be able to be simplified because of the 4 to the third power aspect of it. So just keep that in the back of your mind. Moving along then, when you have an exponent that's a fraction, remember that the denominator of the fraction becomes the index of a radical. And so really what you're saying here is that you want to take the cube root of 27 and then take that number to the 4th power. Now, you could, if you really wanted to, take the cube root of and then do 27 to the 4th first. But because this isn't the calculator part of the test, I would never ask you to multiply 27 to the 4th power without a calculator. In fact, I probably wouldn't do it with a calculator either, just because it's a big, huge number for no purpose other than to make it a small number again. So anyway, so the first thing that I'm going to do is the cube root of 27, which is 3. And then we're going to do 3 to the 4th power, and that's going to give us 81 as an answer. 3 to the 4th power is 81. Now, if you have a negative exponent on a fraction, remember that that flips the fraction over and then makes the exponent positive. And really, when you have a positive, or when you have a exponent on a fraction, what that does is allows you to put that exponent on each part of the fraction. And so the answer here is going to be 125 over 8. And in part D, you've got all 3 things going on here. So notice that you have a negative exponent, you have a numerator, and you have a denominator. You can start with any one of those 3. You can do 9 to the 5th and 4 to the 5th and then take the square root and then flip the fraction, or you can take the square root first and then flip the fraction and then do the 5th power. I like to get rid of the negative first, and so I will flip the fraction first, and that's the thing I just highlighted in pink, that is the negative exponent. So I'm going to rewrite this as 4 over 9, and then leave 5 halves as 5 halves. Now I'm going to look at the square root of both of those. So I'm basically saying the square root of 4/9, and then I'm going to take that answer and take it to the 5th power. And so the square root of 4/9 is 2 over 3, and then 2 over 3 to the 5th power. 2 to the 5th is 32. I would also, if I were you, maybe have in my head 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, maybe even 2 to the 7th, or be able to compute those real fast in the margin. 2 to the 5th is 32 is something that you'll definitely see multiple times on this test. Just at least, at the very least, be familiar with it. And then 3 to the 5th, if you don't know that off the top of your head, you might just say, okay, well, I know that 3 to the 4th is 81, and 81 times 3 is going to be 24. So 3 to the 5th is 243. Or just have 3 to the 5th memorized. It's just not a huge number. So that's some practice with the exponents and simplifying exponents. So here now we get into logarithms. And, sorry, missed one. And just remember, I gave you a very straightforward logarithm problem to start with. And remember that the question that you are wanting to ask yourself about these problems, look at the base. The base of the logarithm is the base of the exponent. And you want to know, what exponent do I put on 3 to give me 81 as an answer? And you should know that 3 to the 4th power is 81. And so your answer there is 4. If you have the logarithm of a fraction, your answer will be negative, because that's what forces numbers into a denominator. And so the log base 4 of 64, again, you're asking yourself 4 to what power equals 1 over 64. And if you remember that 4 to the positive 3 is 64, then 4 to the negative 3 must be 1 over 64. So your answer here is negative 3. And in this one, remember that radicals can be written as a fraction exponent. So this really says log base 5 of 5 to the 1/9 power. And the other thing that you want to keep in mind is that if the base of the log and the base of the exponent are the same, then your answer is just going to be 1/9. It's going to be whatever the exponent is. But if you want to think it through like the previous couple of problems, what you can do is you can say, okay, well, if 5 is the base of the logarithm, 5 to what power is going to be equal to 5 to the 1/9 power? Well, if the bases are the same, then the exponents have to be the same, and so your answer to this is still 1/9. This problem, although it's ugly, is actually the same exact problem. Not the same numbers, of course, but it's the same concept. And so if the base with an, and do you see that 8 is the base to this power? So the base of the exponent is the same as the base of the logarithm. Your answer is just going to be 19. And remember that what a logarithm means is what exponent do you put on 8 to get 19? And if you take that exponent and put it on 8, you'll get 19. Now, you cannot have the log of a negative number or 0, and so your answer to this is undefined. Letter K, I'm sorry, is very similar to letter G, where you have the same base of the log as you do of the number with an exponent. And if you want to think it through, 17 to what power equals 17 to the radical 5 power? And if the bases are the same, the exponents are the same. But if you have the same base for both, it's just going to be whatever that exponent is. And this next one, this is another one that you might memorize. If the base is exactly the same as the input of the logarithm, your answer is just going to be 1. But if you wanted to write that out, you could say 19 to what power gives me 19. And 19 to the first power, any number to the first power is equal to itself. And here you have to remember that log without a written base is log base 10. Remember, that's called common log. If there's no written base, it's base 10. So your thinking here is 10 to what power equals 0.01. And in these cases, you would count the number of decimal places. And because it's a decimal number with a 1 at the end, it's just going to be -2. 2 decimal places, -2. So in letter P, this is just a division problem. So you want to first ask yourself, what's the answer to log base 4 of 64? And that's going to be 3. So this question is asking you to divide 15 divided by 3, and your answer is 5. In letter Q, it does not matter what the base is, and you answered this question on the front page. The thinking is 18 to what power equals 1. And again, it doesn't matter what the base is. Anything to the 0 power is 1, and so your answer to this one is 0. In J, in R, similar to J, the log of a 0 or a negative number is going to be undefined. And letter S is similar to letter P, where you want to start by computing ln of e to the 8th power. And remember that that is log base e of e to the 8th. And if the base of the logarithm is the same as the base with an exponent, then your answer is just 8, but you have to multiply that whole thing by 5, because this really says 5 times ln e to the 8. And so your answer to this whole problem is going to be 40. Now, you can do this problem 2 different ways. You can do it exactly like the previous problem, where we multiply a half times the answer to log base 2 of 64. So that would be 1/2. And if you know quickly that the log base 2 of 64 is 6, you would get 3. Or you can say, let me switch colors here. You can say, look, I know from a topic that we haven't talked about yet in this video, but you know from class, that you can take that 1/2 and make it the square root of 64, 64 to the 1/2 power. So this would be log base 2 of 8. And then the exponent that you put on 2 to get 8 would be 3. So either way, your answer is going to be 3. So 2 ways to do that problem. Doesn't matter. I want you to know that the answer is 3. Now, this problem is similar to letter S in that you should recognize that ln is log base e, and also recognize that 1 over e to the 17th is e to the negative 17th. And when the base of the logarithm is the same as the base with the power on it, your answer is just whatever that power is. So your answer to this one is negative 17. Letter V is similar to letter N, but this time, first of all, remember that it's common log, so you're assuming that if there's no written log, it's log base 10. And this time, when it's a 1 with multiple zeros after it, you're counting just the zeros. And you're thinking to yourself, 10 to what power equals 1,000? And so your answer here is going to be 3. Now, starting with letter W, I would expect that you would need to do some scratch work, like solving an exponential equation to come up with the value of the logarithm. And there will be a couple of problems on the test like this, like W, X, Y, Z, double A. I put a lot of problems in this section, but they're short. So anyway, start with your same process. And remember that you should always have a process for thinking through these logarithms and then do the same thing every single time. So here, my process says, take the base of the logarithm. I'm trying to figure out what power it's raised to that would give me 625 as an answer. And now what I want to do is ask myself, is there a way that I can write the number that's the base with the x on it and the other side of the equation both as a base with an exponent and the same base with an exponent? So it should be obvious to you, hopefully, that both of 1/5 and 625 can be written as 5 to a power. So over here, it would be 5 to the negative 1 power. And over here, 625 is 5 to the 4th power. And take a minute and scratch that out on the side of the page to make sure that you believe me. Now on the left, I'm going to simplify. So I'm going to write 5 to the negative x power equals 5 to the 4th power. Now if the bases are the same, then the exponents have to be the same. So really, I'm just solving the equation negative x equals 4. So x equals negative 4. And so my answer to the logarithm then is negative 4. What I'm going to ask that you not do is write all of this stuff and then not just answer the question. Because this is not an answer to your question. This is an answer to the question. This stuff is just how you figured it out. Let's look at letter X. So again, that one doesn't jump off the page at me, so I'm going to need to solve some kind of an equation. I'm going to need to pull together an equation to solve and use the same process every time. The base of the logarithm to some power that I don't know should equal the input. And so in this case, I'm going to look at both of the 27 and the 81 and ask myself, is there some number that I can use as a base that's the same for both 27 and 81 so that I can just then solve for the exponents? And in this case, that number is going to be 3 because 3 to the 3rd power is 27. Don't forget to write your x. And 3 to the 4th power is 81. So now I have 3 as a base on each side of the equal sign, and so I'm going to just solve for the exponents. 3x equals 4. Notice I did 3x here equals 4 there. And divide both sides by 3, x equals 4/3. And so my answer over here is going to be 4/3. Let's try another one like that. Again, use the same process every time. 32 to the x power equals 8. I want to find a number that I can use as a base with an exponent that would give me both 32 and 8. And so in this case, we just talked about 32 a couple minutes ago. 32 is 2 to the 5th power. Don't forget your x. And 8 is 2 to the 3rd power. And so you're solving, because the 2's are the same, you're solving the equation 5x equals 3. You're solving what the exponents are to be equal to each other. And so x is equal to 3 over 5. So your answer to the problem is 3 over 5. And again, use the same process. So 25 to some power equals radical 5. And I want to find a base that I can get both 25 and radical 5. Hope it's obvious that that number would be 5. So 5 squared is 25. Don't forget your x. Radical 5 is 5 to the 1/2 power. And so I'm solving the exponents to x equals 1/2. X is equal to 1/4. And so my answer to this question is 1/4. Wow, this looks crazy. I don't think I can do it. Sure you can. So start with the same process. 216 to some power equals the 5th root of 6. So you want to find some number that can be the base of 216 and the 5th root of 6. Hint. Might it be 6? Try 6. Just kind of scratch it out on the side of the paper. I know that 6 times 6 is 36. And then 36 times 6, I don't know off the top of my head, but that's not a difficult multiplication problem. 6 times 6 is 36, carry the 3. 3 times 6 is 18, plus 3 is 21. Oh, look, 216 is 6 cubed. So I'm going to come back here. I'm going to write 6 to the 3x power on the left and 6 to the 1/5 power on the right. And so really the only equation that I'm solving here is the exponents 3x equals 1/5. So x equals 1 over 15. 1 over 15. So next we have some expand and condense problems. Notice the directions here that your answer should be the sum, difference, or product of logarithms, and that you have to simplify anything that can be simplified. Real quick note is that your answers to C and F will or should have parentheses in them, but the rest you should eliminate parentheses, meaning that if you can distribute, you need to distribute. But when we get to C and F, we'll talk about why you can't get rid of the parentheses for those problems. So let's start with a fairly straightforward problem here. If you have the logarithm of a multiplication problem, meaning that the thing that's being input into the logarithm, and technically this is called the argument, what I just highlighted in yellow, the argument of a logarithm. If the argument of a logarithm is a multiplication problem, here we have 216 times x, then you want to rewrite that as an addition problem. So log base 6 of 216 plus log base 6 of x. Now, log base 6 of x cannot be simplified any farther. But as we did up above, let's say, in problem AA, we see that 6 to the third power is 216. And so we're going to change this log base 6 of 216 just becomes 3. And the whole answer to this problem is 3 plus log base 6 of x. In letter B, if the argument of a logarithm, and remember ln is a logarithm, it's just log base e, it's just another way of writing a special logarithm, so don't be confused by ln, it's just a logarithm. If the argument for a logarithm has an exponent on it, then we're going to write that as a coefficient. Now, I'm going to show more steps than you are going to need to show for any of these problems, but if you can do some of these combinations of steps in your head, that's great. But I need to see a little bit of something in case you make a mistake. I want to be able to give you partial credit. So anyway, I'm going to rewrite this as 4 ln of, and then that same division problem, y over e to the third. And then the next thing to note is that if the input or the argument for a logarithm is a division problem, that you want to rewrite that as a subtraction. But really, keep in mind that this is 4 times that whole thing. And so when I write my next step, I'm going to write 4 times, and then the subtraction problem, ln of y minus ln of e to the third power. Now, based on what we did up above, you know that ln of e to the third power is just 3. And so really what we're saying here is 4 times ln of y minus 3, right? This here, just a quick reminder, it says log base e of e to the third. What power goes on e to give you e to the third? It's just 3. And the last step, because the directions say no parentheses for letter B, the last step is that I'm going to then distribute the 4 to both of the terms inside of the parentheses there. And my final answer for letter B is 4 ln of y minus 4 times 3, which is 12. Now in letter C, first of all, the biggest problem, the biggest thing happening inside the argument of the logarithm is a division problem. And so I'm going to start with writing out the division as a log minus log, or a subtraction of logarithms. And so this is going to be log base 7 of, and then whatever's the numerator, minus log base 7 of whatever's the denominator. Now, at this point, you can't do anything else, because here the argument of this logarithm is a subtraction problem. And here the argument of this logarithm is an addition problem. And the only time that you can expand part of a logarithm is if you have a multiplication problem like letter A, or a division problem, a multiplication problem like letter A, sorry, the app did something that you couldn't see it do. A division problem like in letter B or letter C, but not an addition or a subtraction problem like is inside of those parentheses. And we're going to see the same thing in a minute in letter F, but just know that your final answer for letter C is just log base 7 of the numerator minus log base 7 of the denominator, and there's nothing else you can do because the numerator and denominator are each an addition or a subtraction problem. Now, in a problem like letter D, what I want to see you do is show me that you know what to do with numerators and denominators when they're in a logarithm more than just a numerator over a denominator. So here I see three things. I see the x, and I see the y, and I see the z cubed. Let's deal with the cubed part last, but let's start with the x, the y, and the z. And the y and the z cubed are both in a denominator. Therefore, they're both going to be minus log. So when I say that, the x is in a numerator, so it's going to be a positive log. So I'm just going to write log base 11 of x. Now, the y is in a denominator, so I'm going to subtract log base 11 of y. The z is also in the denominator, and so I'm going to subtract log base 11 of z cubed. And just make sure that you understand that the y and the z are minus logarithm because they were in a denominator. The only other thing, though, that I have to look at then is the cubed on the z, and you want to expand that just slightly farther. So I'm going to rewrite the rest of it, log base 11 of x minus log base 11 of y minus 3 log base 11 of z. Now, in letter E, you want to break it down slowly. I'm going to start by looking at the radical. I'm actually not going to use my log properties right off the bat. What I'm going to do is try to rewrite this as one big multiplication problem. And I'm going to rewrite that radical, and only the radical. Notice that the x itself is not affected at all by the radical or the cube root. And so I'm going to try to write this as just a multiplication problem where if it has a fraction exponent, it's only a fraction exponent on one thing each. And so, for example, here, I've got log base 6 of x times, and I'm going to take everything here, put it inside parentheses to the 1/3 power. So now what I had highlighted in pink up above from the radical is this. And now I'm going to take that 1/3 exponent and put it on each of the 7 and the y squared. So my next step, what that's going to look like is log base 6 of x times 7 to the 1/3, and then y squared to the 1/3, I'm going to rewrite as y to the 2/3. Notice that that squared does not affect the 7 at all because it was only y squared. Therefore, 7 is 1/3 power and y is the 2/3 power. Now I have three things being multiplied, and so it's going to be log plus log plus log in my next step. So I've got this log base 6 of x plus log base 6 of 7 to the 1/3 plus log base 6 of y to the 2/3. And last but not least, I have to deal with those exponents. And so I'm going to keep log base 6 of x plus, and now the exponent inside the logarithm becomes the coefficient of the logarithm. So plus 1/3 log base 6 of 7. That can't be simplified because there's no power of 6 that gives you 7 as a result. And then plus 2/3 log base 6 of y. And last but not least, in letter F, again, I have several things going on in a numerator and several things going on in a denominator. So let's kind of look at this as four separate things. So I see in the numerator a 5, and I see this whole thing, parentheses to the 4th power, and that is actually not going to be as complex as you might think. And then in the denominator, I see an x to the 7th and a y. So there are going to be four things that I'm going to have to write out with the log. The 2 in the numerator are going to both be positive log, and the 2 in the denominator are both going to be minus log. So let me start by writing that as the addition subtraction problem. So, and it's common log, so there's no written base to the logarithm, so that means it's log base 10. You don't have to write that. So I've got log of 5 plus log of parentheses, stuff inside the parentheses to the 4th power, minus log of x to the 7th minus log of y. Now, once I have written that out, notice that log of 5 can't be simplified any farther, and log of y can't be simplified any farther. But this logarithm of parentheses to the 4th power, and the next one, log of x to the 7th power, the 4 and the 7 can be written as coefficients. So I'm going to rewrite the whole thing again, log of 5 plus, and now I'm going to write the 4 as a coefficient, 4 times log of x cubed minus 2. Keep those parentheses. We're going to come back and talk about that in a minute. Minus, now 7 becomes the coefficient. Sorry, that was my clock. So I rewrote the exponent 7 as a coefficient, and then we said that the log of y cannot be simplified any farther. Now, your eyes may look at the x cubed minus 2 as problematic. But remember that if the argument of a logarithm is an addition or a subtraction problem, and this is a subtraction problem, then you cannot expand this any farther. You can only expand if the argument is a multiplication problem or a division problem or has an exponent on it. And so you are now done with this problem. You can't do any more. Remember, sometimes in math, the hard thing is to know when you're finished, especially when you're talking about simplifying things. So that's your final answer for F. And now some condensed problems. Remember that expand and condense are opposite processes. So the answers that you got for the questions in problem number 8 on the previous page for the expand problems, the answers to those problems are going to look like the questions in condense. And your answers for the condensed problems are going to look like the questions that were in the expand problems. And so the general gist here is that you want your answer to these 6 problems to be a single logarithm, not log plus log plus log or log minus log plus log, but just one logarithm with no coefficient or no written coefficient, or assuming that it's a coefficient of 1. So here, for example, in letter A, the first thing that I notice is that I have coefficients on both of these logarithms. And so the first thing that I'm going to do is rewrite that expression. Instead of using coefficients, I'm going to change the coefficients to exponents. So this will be log base 5 of x to the 3rd power minus log base 5 of y to the second power. Now, I have a subtraction problem, log minus log. And it only works if it's log minus log, just not just log minus a number, but log minus log. And so you're going to take both of the logarithm arguments and turn them into a division problem. So you're going to write one single logarithm, log base 5, of a division problem, x cubed over y squared. Single logarithm, no written leading coefficient. In letter B, I have log plus log, and the first thing that I'm going to do again is notice that I've got a coefficient on each term, and I'm going to rewrite those coefficients as exponents on the logarithm arguments. So I'll start with log base n of x to the 4th power plus log base n of w to the 1/5 power. Now, I'm also going to point out that when you have a fraction exponent, as we've talked about earlier in this video, that's going to be written as the 5th root of w. And so really this says log base n of x to the 4th plus log base n of the 5th root of w. And now I've got log plus log. And so I'm going to take those two arguments and I'm going to multiply them and write that with a single logarithm. So here my answer is going to be log base n of, and then x to the 4th times the 5th root of w. And then in letter C, I've got 3 things. Notice that I have 3 terms. One of them is negative, and that means that y is going to be a denominator. But the other 2 are positive logarithm, and so the z and the x with their respective exponents are going to be numerators. So let me start by rewriting these things with the 3 and the 1/2 as exponents instead of coefficients. So this first term will be log base 2 of x cubed, and then the next term I'm going to leave alone for a minute, log base 2 of y. And then this last term, z to the 1/2 would be the square root of z. We've talked about that a couple of times, so I'm just going to skip the step in between and write square root of z. And now I'm going to take the x cubed and put it in a numerator, take the y and put it in a denominator, and take the radical z and put it in the numerator. And so my whole answer to this question is going to be log base 2 of x cubed radical z all over y. And just real quick again, the x cubed in the numerator because the log was positive, the y in the denominator because the log was negative, and the z in the numerator because the log was positive. And so that's your answer to part C. Now, in part D, remember that up above I had said I've got log minus log, or in B I've got log plus log. And both terms, in both A and B, have a logarithm in them. But in letter D, the first term does not have a logarithm and the second term does. So what we need to do is replace 2 with something that's ln. So the thinking is ln of what equals 2. Remember that ln means log base e, and I want to know, think, e to the second power equals what? That's this swish or the curve or the curlicue or however you learned it. Well, e to the second power is e to the second power. So the thinking there is ln of e to the second power is equal to 2. And so I'm going to replace the 2 here with ln e to the second power minus ln of 9. And your temptation might be, oh, look, I can simplify ln of e to the second power, but don't simplify it because you just unsimplified it so that you could condense the two terms of this question. So now you've got logarithm minus logarithm. And so your answer is going to be a division problem, ln of e squared over 9. In part E, I'll remind you that if the argument of the logarithm is an addition or a subtraction problem, you cannot do anything. You can't change what's inside those parentheses because it's addition and subtraction problems. And so we're going to look at the subtraction overall, log minus log, which means that my answer is going to be a division problem. It's log base 10, or the common logarithm, because there's no written base, so I don't have to write a base. And I've got log of x plus 2 over 6x minus 1. And last but not least, another problem that checks, like the problem directly above it, that checks to see if you know what to put in a numerator and what to put in a denominator. So when I look at this problem, I see that I have 3 terms. I have the negative log base 5 of x to the 7th power that's going to be a denominator. I have the plus log base 5 of 25. Don't simplify that because you need the written logarithm in order to condense this problem. But it's plus logarithm, so the 25 is going to be a numerator. And then I've got this minus log base 5 of y, and that's going to be a denominator. And so the x and the y are going to be in the denominator, and the 25 is going to be in the numerator. Remember to put this 7 here as an exponent on the x. And so I've got log base 5 of 25 in the numerator, x to the 7th, and y in the denominator. And just make sure that you don't write this in such a way that you confuse the 5 here as a coefficient. It's not a coefficient, it's the base of the logarithm. And that's it. You're done with condensing. Now, all of those problems up till now, you should have been able to do without a calculator. And frankly, you might not have even used a calculator for much of it. If you had one available, you probably wouldn't have even taken the cover off of it. Starting with the problems from here on, you will have a calculator. That includes the graphing problems that you've done in class and on the quiz without a calculator. I am going to put those on the calculator section of the test, just to make it a little bit more expedient. I could put these on the no calculator section of the test, and I would be justified in doing so because you've proven to me that you can. Anyway, I'm going to draw the graphs of both 3 to the x and log base 3 of x on the same axes. I'm going to do the 3 to the x power in blue, and on my calculator, I'm going to get a table of values. Remember that we're not using Desmos, by the way. The test will just be with the TI graphing calculators, and I won't let you use your own. You're going to need to use one of the school's calculators without Polysmith, just so you know. So if I'm thinking through the table here, anything to the -2 power is going to be 1 over, so this is going to be 1 over 9, -1 is going to be 1 over 3, 0 is 1, 3 to the first power is 3, 3 to the second power is 9, and you really don't have much more room to graph anything else. So I'm going to graph those values in blue. You can't almost really distinguish the 1/9. The 1/3 is just slightly higher than the 1/9. Here's your 0, 1, your 1, 3, and your 3 to the second power. And remember that with the exponential graphs, there's a horizontal asymptote. And then the graph comes up kind of like this. And so zooming out, that's sort of what your 3 to the x power should look like. I'm going to switch over to red for the log base 3 of x. And again, you're going to give yourself the table of values on the calculator. But remember that anything 0 or negative on your calculator, it says error, but you know in your head that there's no such mathematical value as error, and so it's going to be undefined. But starting with 1, when x is 1, y is 0, and then just look at the whole number values. That'll be sufficient. At 3, you've got the value 1. At 9, you have the value 2. And the next whole number value would be 27 and 3. And that would be off the edge of the graph. So let's just graph those 4 points. So I've got 0, 1, 0. I've got 3, 1. And I've got 9, 2. Now, unfortunately, your calculator can't really handle the logarithmic graph. And so that's about all you see. And remember that if that's what I see on your test, I'm going to take off some points for this section of the graph right here, because you need to know enough that the logarithmic graph actually then goes down toward an asymptote, and the asymptote is a vertical asymptote at the y-axis. And so your graph needs to continue to, it's hard to draw this on my iPad, but it needs to continue down like this. That's probably as good as I'm going to be able to give you here. And so your graph should really give you that feeling of the inverse graphs if you've graphed it accurately. And you don't have to, but if you want to, I know that a couple of you want to give me that line proving that you understand that those two functions are inverse functions. And this is the line y equals x. And it shows you that the exponential function graph and the logarithmic function graph are inverse graphs because they reflect over the line y equals x. Now, what you're going to do for the next couple of problems is type the equation into your calculator and then draw the graph. I'm gonna ask you to graph the points that you can that are whole number points. And I'm also going to ask you to lightly sketch all asymptotes. So remember to draw your asymptotes. So 2 to the negative x is, go ahead and pause the video and type that into your calculator. But 2 to the negative x will have a point at -2, 4, -1, 2, 0, 1, 1, 1/2, and so on. And on the right, it'll get closer and closer to the x-axis. I also kind of, just because I think this way, I know that -3 and 8 would be about there. And so just kind of to give myself a guiding point to shoot for when I'm drawing the graph on the left, I always put that little point kind of faintly up there. Don't do it if you can't be accurate, but it just gives me kind of something to shoot for. And then the graph kind of comes down toward the x-axis. We're going to draw in that asymptote in just a minute. So So there's your graph of 2 to the negative x. And remember that I really want you to show me that you've got some points graphed here, and then put the asymptote in. And in this case, the asymptote is going to be at y equals 0. So the domain of every exponential function is all real numbers, negative infinity to positive infinity. And the range without any transformations or shifts, I guess, is a better way to put it, is going to be 0 to positive infinity because I didn't shift it up or down. There are no x-intercepts because the graph doesn't touch the x-axis. There's an asymptote there. There's a y-intercept at 0, 1. If you look at the graph starting from the left to the right, you can see that it's decreasing. So when asked about increasing, it's not increasing anywhere. It's decreasing over the whole domain. We said that there's an asymptote at y equals 0. And remember, the end behavior asks you as x goes to positive infinity, what is the function approaching? And as x goes to negative infinity, what is the function approaching? And so you need to answer those two questions. And so here, really what this says is, on the right, what's happening? Well, on the right, the graph is going toward the asymptote. And so on the right, the asymptote is 0. And so remember that a horizontal asymptote always is about end behavior. Horizontal asymptote about end behavior. On the left, so the second part of the end behavior asks about the left. On the left, the graph is going up. And so the left end behavior is infinity. Now, in the second one, pause the video for a minute and put log base 2 of x plus 2 into your calculator. And if you have forgotten how to type log base 2, you do alpha, window, and then just hit the number 5. And it'll give you log with a little box down here where you're going to type the base. And then I think parentheses with a box up there that's going to give you a place to type the argument. So you've typed log base 2 of x plus 2. And then you want to pull up the table of values that you're going to be graphing. And it gives you a point at the first x value that it gives you that's not an error is the point -1, 0. It gives you a point at 0, 1. It gives you a point at 2, 2, and a point at 6, 3. And again, like I said, for one of the problems above, if you just look at the graph in the calculator, you don't get a whole lot more than this. And what I expect you to do is to know that this graph shifted to the left 2. And whereas in the parent function, the asymptote is at 0, in the transformed function, the asymptote is at -2 because it shifted to the left from 0 to -2. So there's your asymptote at -2. And I expect you to know that you continue drawing the logarithmic function toward the asymptote here and show that it keeps going. Now, the domain of a logarithm has a restriction. Remember that the 3 domain restrictions are x in a denominator, x inside a square root, and x as an argument for a logarithm. So there's a restriction on the domain. This restriction is affected by the shift to the left. And so my domain here is going to be, my domain here is going to be -2 to positive infinity. All logarithmic functions have a range of all real numbers. My x-intercept here is -1. My y-intercept here is +1. And hopefully you can see as you look at the graph that the entire graph is increasing. And so this graph is increasing over the domain. And notice in both the decreasing interval for letter A and the increasing interval for letter B, that those numbers, the -2 to infinity here, the -infinity to -infinity here, all match the domain. So whether it's increasing or decreasing for exponential and logarithmic functions, it'll match the values in the domain. And whether it's increasing or decreasing, the other is going to be none. We said that there's an asymptote here. I failed to write the equation for the asymptote. That's going to be x equals -2. A vertical asymptote has x equals. And so my asymptote for this graph is x equals -2. And remember that when we ask you about end behavior for a logarithmic function, there's only end behavior on one end, that nothing is happening to the graph over here. And the end behavior talks about infinite end behavior, as the graph goes infinitely left and infinitely right. So in this case, there's only infinitely right. So when I talk about the end behavior of the logarithmic function, in this case, as x goes to positive infinity on the right, the graph is going up. So the answer is going to be positive infinity. And then there's no left end behavior for letter B. In Unit 9, we're going to talk more about the notation of the approaching, that little arrow that I always read as approaching, in a unit about limits and continuity of functions. And we're going to talk about this infinite end behavior further. So this page will completely be about solving equations. Remember that the most basic thing about solving equations and the word solve is that your answer, if the question in a math class is solve, your answer has to be x equals a number. You're not simplifying, you're not simply rearranging, you are actually figuring out what x is equal to. So in class, we've talked about, like for example, in the first problem, would I use 2 as a base or 4 as a base? What if I did it differently than you? If you do a whole bunch of mathematical steps and your math from step to step makes sense, the chances of you randomly getting an accurate answer based on some not good math, either mean you cheated, or that you understand the math and you just took a different route to the same answer than I did. So having said that, you might look at letter A and remember that the goal here when you have an x in an exponent is to see if you can take the base on each side and rewrite it as the same base with a power, so that you've got the same number raised to an exponent on each side of the equation, and then set the exponents equal to each other. And if the first thing you see is 2, 8 is 2 to the 3rd power, and 64 is 2 to the 6th power, and you are welcome to do that. But the way that I'm going to work this problem out is I see that both 8 and 64 are 8 to a power. That helps me work with some smaller numbers. So now I have, on the left, I'm going to leave the 8 and the 3x plus 2 the way they are and change 64 to 8 squared. Again, you'll get the same answer if you use 2 as the base. You're just going to have some numbers that are slightly bigger. Not even a lot bigger, just slightly bigger than the ones that I'm using here. But now that I have both of these bases the same, I'm going to set the exponents equal to each other. And so the equation that I'm solving really is just 3x plus 2 equals 2. Subtract 2 from both sides, and x equals 0. In letter B, remember that if you have a logarithm, a single logarithm with nothing else around it, already isolated on one side, equal to a number on the other side, all you need to do then is take the base of the logarithm with that number as an exponent on it equal to the argument of the logarithm. Remember that a log without a written base is the common log, so that's base 10. And so here, I'm going to say 10 to the third power equals 0.005x. And I'm going to divide both sides by 0.005. And when I do that, I get x is equal to 200,000. And I don't care about the comma. Just make sure you get the right number of zeros either way. Now, in letter C, you have a base with a power, and you have the x that you're solving for in the power or in the exponent, and therefore you want to isolate the part of the equation that has that exponent on it. And so I'm going to start by subtracting 7 from both sides. So I have 2 times e to the 3x minus 5 equals 520. I started to write it wrong. And then I'm going to divide both sides by that 2. So I still have e to the 3x minus 5. And then 520 divided by 2 is 260. And whenever you have an exponent that has an x in it and you want to get the x out of the exponent, and there's no way that I can write 260 as e to a power. I can't make those two bases equal to each other. What I'm going to do is take the ln of both sides. So I'm just going to put ln of both sides. And so in this case, it's going to be ln of e to the 3x minus 5 equals ln of 260. And you should remember that when you have ln, which is log base e, of e to a power, that whole entire left side of the equation is just the power. So 3x minus 5 equals ln of 260. So this next part, because you don't want to compute ln of 260, round it, and then use your rounded answer to compute your next answer, what you're going to want to do is type the whole solution to this problem into your calculator in one step. And so notice that you know at some point you're going to need to add 5 and then divide by 3. And so let's write it like that. Let's write x equals ln of 260 plus 5 divided by 3. And then this is what you type into your calculator. Make the fraction in your calculator using alpha y equals enter. ln of 260. When you do that, remember that your calculator starts with open parentheses. You have to close the parentheses right there. So ln of 260, close the parentheses first, then plus 5, that's your numerator, all over 3 in the denominator. And you should get x equals 3.52. Remember that Applebacher wants 2 decimal places, rounding to 2 decimal places. So letter D is a lot like letter B, where you have a single logarithm on one side and that equal to a number on the other side. Remember that ln is the same as saying log base e of whatever's inside the parentheses is equal to 9. And so I can go ahead and rewrite this whole entire thing, and again, using the curlicue or the swish or however you want to look at that, as e to the 9th power is equal to that whole expression 5x minus 1. Now, e to the ninth power is a number. E is a number, 9 is a number to a number power. It's an ugly decimal, big, huge, awful number, but it's still a number. And so if I want to isolate in this equation, if I want to isolate the x, which is really what we're doing when we're solving an equation, is getting x by itself, then at some point I'm going to have to add 1 and divide by 5. So rather than computing e to the ninth first, getting a big ugly decimal number, rounding it, and then using a rounded number to compute an answer, which we never want to do, what I'm going to do is say that x is equal to e to the ninth plus 1 divided by 5. And in that case, then, this is what I type into my calculator. So go ahead and use the fraction function in your calculator, alpha y equals enter, and type e to the ninth. Remember that to get the e, by the way, you do second, and then that button on the left that says ln, and it gives you e with the cursor ready to type an exponent, because e always comes either as part of e with an exponent or the base of a logarithm. That's the way that e is used. And so type in the numerator e to the ninth power plus 1, and then in the denominator 5, and round to 2 decimal places because Miss Applebacher is your teacher, and you get x equals 1620.82. Now in letter E, my thinking here is that I can rewrite 0.25 as a number that has 4 as the base. So let's leave the left-hand side alone for a minute. And remember that 0.25 is 1 over 4, and 1 over 4 is 4 to the negative 1 power. So now I have 4 to the negative 3x equals 4 to the negative 1 power. Now I have the bases on both sides the same, and so my equation is going to be to solve to make the exponents equal to each other. And so x is equal to negative 1 divided by negative 3, which is positive 1/3. And in letter F, letter F is just like letter B and letter D, where you have a single logarithm on one side, no coefficient, no anything else being added or subtracted, equal to a number on the other side, and you're just going to say 7 to this power is equal to x. And so it's going to be 7 to the radical 6 power, yes, I know it's ugly, equals x. So all you have to do is type that into your calculator, 7, and then use that caret button, radical 6, and you should get that x is equal to 117.51. Now, in letter G, the first thing that you should notice, hopefully, is that you've got the logarithm of a negative number, and you can never take the logarithm of a negative number. Therefore, no value of x is going to give you all of this over here, and so your answer is no solution. Now in letter H, what I want to do here is to isolate the logarithm. Remember, ln is a logarithm, and 7x is the argument for that logarithm, so it's got to stay with that log. So I'm basically going to look at subtracting the 5 and dividing by the 2. And so 2 times ln of 7x equals 23 minus 5, which is going to be 18. And then ln of 7x is going to be 18 divided by 2, which is 9. And remember that your thinking here is that this really says log base e of 7x equals 9, and just rewrite that as e to the 9th power equals 7x. And in order to type this into my calculator, I'm going to type in e to the 9th divided by 7. When I type that in, I should get that x is equal to 1157.58. Now, in letter J, what we have here is an x in an exponent. But this time, unlike problems like problems like letter A or letter E, in letter A and letter E, what I could do was force the bases with the exponents to be the same. In number 1, I used 8, or you could have used 2, and in letter E, we used 4. You probably could have used 2 in letter E as well, and you'd still get the same answer. But here, there's no way that I can make 5 or 17 have an exponent on them so that it's the same base with an exponent. So there needs to be a different way to solve this equation. And so in this equation, what I'm going to do is take the ln of both sides, and I did that up in letter C. And so really what I have here then is ln of 5 to the x equals ln of 17. Now, unlike letter C, where the left side in letter C was e with a power on it, in this case I don't have e with a power, but what I can do is take the x and write it as a coefficient, and thus it's no longer an exponent, it's actually a number just being multiplied by something. And so my next step here is to rewrite that as x times ln of 5 equals ln of 17. And remember that ln of 5 is a number and ln of 17 is a number. There's no other variables there. So this is x times something equals something. And if x is multiplied by something and I want x to be alone, then I just rewrite the whole thing as a division problem. I divide by ln of 5 on both sides so that the ln of 5 on the left is canceled, and I end up with x equals the fraction ln of 17 divided by ln of 5. And again, type it into the calculator just like that, ln of 17 divided by ln of 5. I personally would use the fraction function in the calculator, but you can just use the divide sign. Remember that you want parentheses around the 17 and around the 5. If you don't, it'll mess up your division. And what you should get ultimately for your final answer is 1.76. Now, letter K, I'm going to do on a separate page. So let's say work on a separate page, but I'm going to do this later in the video. Right, page. After, in the video, it's going to be timing after part P at the bottom of this page. So just kind of set that aside, and if you want to do this problem on a separate sheet of paper, that also works because it's going to have a lot of steps to it. Now I'm going to move directly to letter M. And in these problems, if I have a single logarithm on each side of the equation, I can go ahead and set the arguments equal to each other. But in this case, on the left, I have log plus log. And if you only look at the left side of the equation, because it's log plus log, I can rewrite that as a multiplication problem. So logarithm of a multiplication problem, and just bring the other side of the equation down. And now I have log of something equals log of something. And because the logarithms are equal, you can assume that the arguments are equal. So really my next assumption is x times x plus 7 is equal to 18. That's going to be x squared plus 7x equals 18. I'm going to subtract 18 from both sides. And then I'm going to factor. And then I'm going to solve each of the factors for 0. So x equals -9 and x equals +2. But remember that you have to check for an extraneous solution. Make a little note of that to yourself, that you have to check for extraneous solutions. And so in this case, I can't use -9 because -9, ln of -9 would not be a solution to this equation. Whereas ln of +2 works here, and doesn't change ln of 18. So x equals 2 is your good solution, and x equals -9 is extraneous. And what I would like for you to do is write that a solution is extraneous. Now, in letter N, notice that you have 3 terms, 2 on the left side and 1 on the right, that you have to manipulate. And in this case, one of those 3 terms is not a logarithm. Now, there are other ways that you can correctly solve this problem, but what I'm going to choose to do here is using the same concept that we did when we were condensing logarithms using the logarithm properties. I'm going to change this 2 to something that has log base 9 like the other logarithms in the problem. So I know that log base 9 of 81 is equal to 2. I'm going to rewrite this whole problem as log base 9 of 9x minus log base 9 of 81 equals negative log base 9 of x. Now, like I said, there's other ways that you can start this problem, but to me that just seemed like the most obvious, to make everything as a logarithm. And now I can rewrite the left side as a division problem. So here on the left, I'm going to say that this is log base 9 of 9x over 81. Now on the, did I say on the right? This is on the left. On the left, I'm going to write that as log base 9 of 9x over 81. But on the right, I'm also going to deal with the negative here, and I'm going to rewrite the right-hand side as log base 9 of 1 over x, and that's x to the -1 power. Now, because I have a single logarithm equals a single logarithm, and neither of them have coefficients, I can just set the arguments equal to each other. So this whole problem becomes 9x over 81 equals 1 over x. I can solve that using cross products. So I'm going to multiply the 9x times x and get 9x squared, and 1 times 81 is 81. Divide both sides by 9, so x squared equals 9. And then x equals plus or minus 3. Now, don't put a box around your answer and move along. Remember that you need to check for extraneous solutions like we did in the previous problem, because hint, hint, there's going to be an extraneous solution here. So I think through both answers. +3, 9 times +3 is +27. positive 3 there. Both of those numbers are fine as arguments for logarithms. But if I take the negative 3, 9 times negative 3 is negative 27, and I can't do log of negative 3 either. And so in this case, you want to indicate that, that x equals 3 is your solution, and that x equals negative 3 is extraneous. And these two problems at the bottom of the page also involve properties. So letter O and letter P are similar to letter N. So let's take a look at this. On the left side of this problem, I see that I have log plus log. And so I'm going to rewrite the left as ln of, and then a multiplication problem, x plus 2 times 3x minus 2. And that whole thing just equals that ln of 4x squared that I have on the right. Now you're going to need to FOIL x plus 2 times 3x minus 2. So go ahead and start multiplying. And when you have multiplied, you should get ln of 3x squared plus 4x minus 4 equals ln of 4x squared. And because now you have a single logarithm equals a single logarithm with the same base, you can drop the logs and just say here 3x squared plus 4x minus 4 equals 4x squared. It's a quadratic equation, and thus you want to get one of the sides equal to 0. And although it looks like it takes more steps, I would take all three of these terms and move them over to the other side so that the 0 is on the left. So that I end up with 0 equals, because 4x squared minus 3 squared is positive 1x squared, that gives me that positive leading coefficient. And then minus 4x and plus 4. And then I'm going to factor that, and I have x minus 2 times x minus 2. And x equals 2 and x equals 2 is the same answer. And real quick, I want to check to see if anything's extraneous. If I put the 2 into this, 2 plus 2 is 4. If I put the 2 into here, 3 times 2 is 6, minus 2 is 4 again. And here, 2 times 2 is 4 times 4 is 16. So in no case does it make the argument of the logarithm equal to 0 or a negative number. And so x equals 2 is a good solution. And then in letter P, once again, I notice that I have logarithm and logarithm, but one term is not a logarithm. And so I want to remember that the common log is the log written without a base, and so that's base 10. I want to rewrite the 3 as log base 10 of something, and that's going to be 1,000. It looks like it's going to be big, huge numbers, but it actually isn't so bad. Once you pull the problem together, it's not going to end up being quadratic like the previous one. So here now I have on the left log of x minus 10 equals, and then I've got that log of 1,000 plus log of x minus 3. And on the right, now I've got log plus log, so I'm going to change that to an addition problem. So here, I'm going to do log of 1,000 times x minus 3. And on the left, just bring down the log of x minus 10. And now I have both sides of the equation with a single logarithm, and so I can drop the logarithms and just say that x minus 10 is equal to 1,000 times x minus 3. distribute the 1,000 on the right, so x minus 10 equals 1,000, x minus 3,000. And then I'm going to subtract x from both sides and add 3,000 to both sides, and I end up on the left with 2,990 equals 999x. And then divide 2,990 divided by 999, and you'll get x equals 2.99. And so in a minute, we're going to turn the page, and I will work out letter K on a separate couple of minutes of the video. Okay, so let's take a look at letter K. And again, I'm going to point out a couple of things that you want to keep in mind, or that you want to look for, is that you see that you have x's in exponents, but that your bases, the 4 and the 7, cannot be written as some other number to a power, so that both sides have like 2 to a power or 3 to a power or 4 to a power. You can't have the same base on both sides. Therefore, the next step has to be to take the ln of both sides. So you're going to do ln of both sides of this equation, and so now I've got ln of 4 to the 3x minus 1 equals ln of 7 to the negative x plus 2. The reason that you do a logarithm of both sides is because when you take a logarithm of something with an exponent, you can rewrite that exponent as a coefficient. And in this case, you're going to rewrite the exponent on both sides as a coefficient and make sure that you use parentheses. So I'm going to rewrite the left side as 3x minus 1 times ln of 4. And I'm going to rewrite the right-hand side as parentheses negative x plus 2 times ln of 7. So now that I have the ln of 4 and the ln of 7, remember that this is a number. It's just a number. It's an ugly number, but it's just a number. And so I've got a number multiplied by an addition or subtraction problem that's in parentheses. And so I'm going to take the ln of 4 and distribute it, and I'm going to take the ln of 7 and distribute it. And when I distribute here, I get 3x times ln of 4 minus 1 times ln of 4. That's the left. And then on the right, I'm going to get negative x times ln of 7 plus 2 times ln of 7. Now, the next thing that I want you to notice is that you've got 4 terms, 2 on each side of the equal sign, and that 2 of those terms, the 3x ln of 4 here and the minus x ln of 7 here, those 2 terms have x's in them. And your other 2 terms are strictly numeric. They do not have any kind of variable in them. And so what I'm going to do is I'm going to rearrange this equation so that the numeric terms are on one side of the equation and the terms with x's in them are on the other side of the equation. So when I do that, what I end up with is on the left, I have that 3x ln of 4, and I'm going to bring over the x ln of 7, but it's going to be plus x ln of 7. And then on the other side, I'm going to keep that 2 ln of 7 and then bring over the ln of 4 so that it's plus ln of 4. Now, take a look at the left. On the left, you have both of your terms with the x's. That's why you brought them over there. And you want to factor out the x like a GCF. So I'm going to pull that x out of each of the terms. And in parentheses, then I'm going to write the terms without the x. So 3 ln of 4 plus just ln of 7. And don't change anything then on the right. I'm just going to leave the right as 2 ln of 7 plus ln of 4. Now basically what we have here is on the left x times a number. This whole thing in parentheses, the 31, listen to me. The 3 ln of 4 plus ln of 7, if you type that whole thing into your calculator, you would get a number. It would be an ugly decimal number, but it's just a number. So you've got x times a number is equal to a number. And so in that case, you can just divide by the number that's multiplied by x. You can divide by that on the other side of the equation, and you'll get a numeric answer. So I'm going to rewrite this in the way that I'm going to type it into the calculator. So x is equal to, I'm going to start with this side because that'll be my numerator, 2 times ln of 7 plus ln of 4 all over 3 ln of 4 plus ln of 7. Now, when I type that into my calculator, what I'm going to do is use my alpha y equals enter to get the fraction, and then type in the numerator and denominator. But keep in mind that the calculator uses more parentheses than we use when we're writing. And so you're going to need to close those parentheses because there's no way to type ln or logarithm in your calculator without having the calculator insist that you give it open parentheses. And therefore you have to tell the calculator where to close the parentheses. So put parentheses around the 7, put parentheses around the 4 in the numerator, put in the denominator parentheses again around the 4 and again around the 7. Type that whole thing into your calculator. And what you should get is x equals 0.86, rounded to 2 decimal places. And that should be your answer for letter K. Last but not least, the applications of exponential and logarithmic concepts to real-world situations. Let's start with the compound interest formula. And before I get too far down the path, please note that you will be given on the test, directly on the test, not even a formula sheet or anything, but you will be just given these formulas, but you need to know how to use them. So as if this review guide were the test, I'll give you this formula here and then give you this problem here, and then you have to figure out what to do with all of that information. In other words, you need to know what to substitute for P, you need to know what to substitute for R, you need to know what to substitute for N, and so on. So let me get rid of the messy yellowness here, and let's start talking about that P, R, N, and T. So in this first problem, it says that over the summer you make $3,000 and you're going to invest all of it. And so the $3,000, that's your P, that's your principal. And the interest rate of the account where you are investing it is 0.9%. That's R, but remember that R has to be written as a decimal and not as a percent, and so you're going to rewrite that as 0.009. You're going to move that decimal point over 2 places. Now, there's 2 other important concepts that you need to know here, and that the interest is computed or compounded, meaning that you're earning interest on your interest, so that if you leave the money in the account so that it gains, so that the interest is computed more than once, that interest will be put into the account on top of the principal, and then the next time they compute interest, you're earning interest on your interest, and that word compounded implies earning interest upon interest upon interest. So the interest is compounded semi-annually, and that's your n value. So n equals 2. Semi-annually means twice a year. And then the last number that you need to know what it is the t, and t is how many years. And so in this case, t is equal to 10 years that you're going to leave the money in the account, and that all the interest is going to be put back into the account, and then the new interest is going to be computed based on the current amount of money in the account, which means you're going to be earning interest on the interest. So that whatever interest you earn in the first 6 months is going to have interest computed on it at the end of 12 months and a year and a half and 2 years and 2.5 years and 3.5 years and so on, 20 times over the 10-year period. So when you substitute into that formula, the amount at the end of 10 years is going to equal your $3,000 principal, there's your P, times 1 plus, and then we said R is 0.009 all over the number N, which is 2, and then the exponent, I'm going to have to squeeze this in here, 2 times 10. And that 2 times 10 says that we're doing this 20 times over the 10-year period. Twice a year for 10 years is 20 times, and that's why the exponent is 20. And you can literally type this entire thing into your calculator just like this, exactly like this. So use the open parentheses and the closed parentheses. Use the fraction for the 0.009 over 2. Use the exponent for the 2 times 10. And then just hit enter. And what you should get is that A is equal to $3,281.86. So $3,281.86. In part B, instead, you're taking that same principal, so the $3,000 is your principal, and put it into an account that compounds your interest quarterly. And so whereas in part A, your N value is 2, here your N value is going to be 4. It's going to compute the interest 4 times a year. And you're going to have the same interest rate. So here your R is still going to be equal to 0.009. And this time you're going to leave the money in the account for 15 years, so T is equal to 15. This time when you substitute into your equation, the amount after 15 years, that's A, is equal to 3,000 times 1 plus, and then that's going to be 0.009 divided by 4, close parentheses, 4 times a year for 15 years. And notice that that means that you're going to have the interest computed 60 times in 15 years. That's a lot of times that you're computing interest on interest on interest. You can type this into your calculator exactly as is with the parentheses and with the fraction. And when you hit enter there, what you should get is that A equals $3,433.09 after 15 years. Now, if computing interest more times a year so that you're earning interest on your interest more than once a year, or more than twice a year, or more than 4 times a year, what we can do is talk about using a continual or a continuously compounded interest, so that you could use, and this is kind of a calculus concept, but you could say, okay, well, it would be better to compound the interest monthly, because that would be 12 times a year, or daily, that would be 365 times a year, Or hourly, that would be 365 times 24 times a year. Or what about just continuously? And if you're continuously compounding the interest, then you would use this formula, A equals P times e to the RT power. And in this case, R is still the interest rate, and T is the number of years. And using E is the thing that accounts for the fact that you are doing it continuously rather than a certain limited number of times per year. So let's say here that you earned $250 doing whatever it was that you were doing. That's your principal. I think my house has more bells and whistles than I realized until I started making videos. So your principal is the $250 that you earned helping your family's friend move. And then you are going to use a account that has the interest compounded continuously, and the rate is 1.2%. And remember that you have to move the decimal point over. So here your R equals 0.012. And the time that you're going to leave it in the account is for 15 years. So your T is equal to 15 years. And so here, when you substitute this into the formula A equals PRT, A equals the $250 times E to the RT power. So your exponent is going to be 0.012 times 15. And you're going to type that into the calculator again as is. You're going to make sure that you put the 0.012 times 15 as the entire exponent on E. And remember that to get E, you're going to type seconds ln to get E to whatever power, and then you fill in that multiplication problem for the power. And when you've done all of that, you should get the answer of $299.30. Now, all three of these problems that we've done so far basically just say to you, here's an amount, here's an interest rate, here's what the compounding is doing, and here's the amount of time that you're leaving the money in the account. But 14B works a little bit differently. So you still have the $250, and you still have the account that has the 1.2% interest on it. But the question is asking you to solve for the time. You can see the way it's worded that it says how long would you have to wait, how many, and it's going to be years because T is given in years for these equations. So using that same information, how long would you have to wait? And it tells you the end amount. So in this case, A is equal to 400, and you don't know T. And so when you fill in the equation, then you're going to say, okay, instead of A, I'm going to write 400 equals, my principal is the same, so that's going to be 250 times E to the, and then I've got that 0.012 times T, which I don't know. And what I have to do now is solve this equation, given that my variable that I'm solving for is an exponent. So let's start by getting E to the power all by itself on the one side of the equation. To do that, I'm going to divide both sides of the equation by 250. And let me leave that left-hand side of the equation for now as 400 over 250. And we'll come back to that in a minute. But what I'm going to do now is take the ln of both sides. So I've got the ln of 400 over 250. And on the right, because I have ln of e to a power, that whole thing is just equal to the power. So ln of 400 divided by 250 is equal to just 0.012 times t. Now, in order to get the t by itself, because remember that you want to solve for t, I am going to divide both sides of the equation by 0.012. So t is going to equal ln of that big ugly fraction, 400 divided by 250, all over 0.012. And I'm going to type exactly that into my calculator. Remember that the calculator is going to give me the open parentheses when I type ln. And you're going to put a fraction to start with for the ln over the 0.012. You're also going to use a fraction for the 400 divided by 250. Right arrow to close the parentheses, and then down arrow to type the 0.012. And then t is going to equal 39.17 years. Now, the other thing that you can expect on your test is that I will give you a growth or decay problem, and I will give you the basic generic formula, and you have to decide where to substitute both the initial amount as well as the final amount, and know what to do with the K value, the rate of either growth or decay. Just as a side note, for those of you who are on top of all of this, do you kind of notice that the growth and decay formula here that I just highlighted green is actually very similar to, and in fact is exactly the same as the continuously compounded interest formula, where the initial amount is the P and then e to the rate times time. That's the same as this formula. So there's really just the one formula for these exponential situations. So let's take a look at the population of Belarus, which is decreasing. The current population is 9.5 million, and so what you want to do is earmark the 9.5 million as y sub 0. And don't write 95000 with a bunch of zeros, just use 9.5, and then million is your units, people, of course. And then the population rate decrease is 0.15%, but remember that the decay is when you have a negative exponent, and so that rate is going to be negative 0.15%. And so you're going to change the negative 0.15%, that's R, to a decimal, so it's going to be negative 0.0015. That's your R value, and it asks you to do two things here. First of all, you're going to write a formula that's in this format that's given up above. And the second thing is, after how many years will the population decrease by half? So the assumption is that you're going to use the formula that you create to then compute how long it's going to take for the population to decrease by half. So your formula, remember that the format is that y, that's basically your f of x. Y is equal to the initial population, y sub 0, times e to the k, which is your rate, times t, which is your time. And let me stress this again. Y is like f of x here, So that's your just your general y value, and t is like x. It's your input and your output, or your domain and your range. E is a number, k is a number that we're given in the problem, and y sub 0 is a number that you're given in the problem. So really you're just dealing with an input and an output, and it's an exponential function because the input is in the exponent. So let me rewrite this using y sub 0 and the r that are given in the problem. Oh, and I wrote r and it should have been k. So let's change that and we'll fix this, and we'll call this k over here. My apologies. So k here is the negative 0.0015. It's the same idea, it's the rate. But I need to be consistent in my use of letters. Y is going to stay Y. Y sub 0 is that 9.5. E stays E. And then your exponent is that negative 0.0015. And then T stays T. So that's your formula. It asks you to give a formula, and so that's the formula. Given that 9.5 million is the current population, or y sub 0, and that population is going to be going down at 0.15%. And so then I am going to use that to solve when the population will be half of that. And so what you want to do is you want to take y, the resulting population, and make it half of the 9.5. So in your calculator, just do 9.5 divided by 2, and you should quickly see that you're looking to see when the population is going to be 4.75 million people. And you're going to solve this equation for t. So I'm going to divide both sides by 9.5 to get that e by itself. Because you computed 4.75 based on being half of 9.5, then what should happen is that you get 0.5 over here and just e to the negative 0.0015t over here. And now you're going to take the ln of both sides. So I have ln of 0.5 is equal to ln of e to the big ugly exponent. But because it's ln of e with an exponent, on the right then I can just make it the exponent and get rid of the ln and the e. So here on the left I have ln of 0.5 is equal to negative 0.0015t. And to solve this equation, t is going to be equal to ln of 0.5 divided by negative 0.0015. Type that into your calculator, and you should get 462.10 years. And remember that Applebacher really always wants units labeled on a problem like this. And now, last but not least, a Richter scale problem. So here you're given the formula. R equals, or R is the intensity on the Richter scale. R equals log of A divided by T plus B. A is the amplitude, T is the period, and B is the factor that modulates the equation to fit based on the weakening of the seismic waves. Honestly, I don't really know what seismic waves weakening, how they compute that exactly, but we're given those numbers. And so here in a certain area, one might expect to see a magnitude 7 earthquake every 500 years. Determine the amplitude of an earthquake. So you're looking for the amplitude, that's A. You're solving for A. You're solving for A. Whose intensity is 7.0. Wait, that's your Richter scale, so that's R equals 7.0. So 7 on the Richter scale with a period. So your period is 3.7. So T equals 3.7 and B equals 2.8. So you are going to use the equation from up here, R equals log of A over T plus B. And so we are told that R is 7, and we are solving for A. T is 3.7, and B is 2.8. So to solve this equation, I want to get the logarithm by itself, and so I'm going to subtract 2.8 from both sides. And so 7 minus 2.8 is 4.2 equals the log of A over 3.7. And what I want to do then is rewrite this. Remember that that log is log base 10. And so I'm going to do 10 to this power equals that thing over there. So 10 to the 4.2 power is equal to A over 3.7. And to get A by itself, I'm going to multiply both sides by 3.7. So 3.7 times 10 to the 4.2 power. And that whole thing is A equals 58,641.05. And again, Applebacher loves units, and so it tells you up here that the amplitude is given in microns. And so in my answer, I'm going to write microns.